Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In our previous lecture, we had seen the implications of 18 valence electron rules. We had also observed the classification that various organometallic compounds show based on this 18 valence electron rule, and also we had looked at the complexes that deviate from the 18 valence electron rules. We have studied these rule in the perspective of molecular orbital theory, particularly looking at the frontier orbital interactions of the metal with the ligand. In our discussion on understanding the molecular orbital correlation diagram representing each of the classes of organometallic compounds, that is of class 1 type, class 2 type and class 3 type, what came to the fore was the fact that organometallic compounds generally exhibit two kinds of interaction. One is a sigma type interaction which occurs between the ligands or atomic orbitals with that of the metal orbitals of similar symmetry. And the other thing that emerged out, which is something very special for organometallic compounds, is the pi interaction that also occurs between metal atomic orbitals with the pi type ligand orbitals of appropriate symmetry. Now, these two features are very unique to transition metal organometallic compounds, and these arise because of partial occupancy of the inner d orbitals at the metal center. Now, in our last few lectures, looking at the valence electron rule and their deviations as well as their classifications, what we had focused on was on the metal center of the metal carbon bond. So, the last few lectures had focused on the metal and the requirement, electronic as well as steric requirement of the metal center that affect the metal center bond. Now, in next few series of lectures, we are going to look at the ligand requirement in terms of what kind of bonds they make with the metal center that affect the organometallic compounds and their classifications. So, to start with, in this lecture we would be discussing the most basic of the ligands of the organometallic compounds, and these are sigma donor ligands. What does this mean is that these ligands have sigma orbitals which involve in bonding with the metal center. So, the focus in this lecture would be on the various types of sigma donor ligands that they come along, how they are prepared, preparations, of organometallic compounds having sigma donor ligands, and then we would look on the properties of sigma donor ligands. Transition metal complexes of sigma donor ligands. This will bring us to an important topic that is very sensitive to organometallic compound, that is their stability. So, we would also discuss in this lecture the thermodynamic stability of these compounds versus their kinetic lability. What I must mention over here, that the carbonatic compounds being extremely sensitive to air and moisture, difficult to handle, there is a false perception that these compounds are largely unstable thermodynamically, but in reality what has been found out, that these compounds thermodynamically are stable, but their reactivity or high reactivity are of kinetic origin. And we will try to look at organometallic compounds from this perspective and understand their high reactivity that arises from their kinetic lability. Lastly, we are going to touch upon a very interesting topic which is of contemporary interest, that is the interaction of CH bond with transition metals. We would look at this topic with very closely based on the fact that this is an important area of contemporary research. Currently, this area is called as CH activation. This is a challenging area as CH bond strength is very high, high bond energy, and CH bonds are ubiquitous. So, they are very common, they are very stable bonds and they are very common, and hence the selectivity in activating them becomes very challenging. And as a result, CH activation is an important area which can result in selective functionalization of the CH bond and can make value added chemicals. So, CH activation initiates with the CH interaction with transition metal compounds, and we are going to look at how does a CH interact with a transition metal during this course of this lecture. Now, with that prelude, let us take a look at how many types of sigma donor ligands are there. Now, the sigma donor ligand depends on hybridization of the carbon center, hybridization. So, for sp3 carbon, one can have compounds which are of this type, metal bound to Cr3. These are called alkyl complexes, or metal alkyls. Now, when the compound is in this way, the way it is drawn, then this kind of binding is called terminal binding. So, ligand is a terminal ligand, this alkyl ligand is a terminal ligand. Alkyl ligand can also bridge and become a bridging system. If it bridges between two metal center, then that can be represented as shown over here. So, alkyl bridging between two metal center, and these are designated as 3 center mu2 alkyl. Mu represents bridging between two metal centers, that is why it is mu2. Now, instead of Cr3 bridging between two metal center, it can also be alkyl moiety of the type Cr2 bridging analogously between the two metal centers, and these are called mu2. Again, mu means bridging, 2 means between the two metal center, alkylidene. And it can be such that instead of Cr2, one can have alkyl moiety of the type Cr bridging between 3 metal centers. And this likewise would be called mu 3, now that there are 3 metal centers, alkylidene. YNE, alkylidene. So, the difference being we have a dy versus d in, rest, and mu 2 versus mu 3, rest all remaining the same. So, what we saw is that sp3 carbon, which will represent a metal alkyl ligand, can act as a terminal ligand, where metal is directly bound to the alkyl, and alkyl is bound to only one metal center. The alkyl can even bind to more than one metal center. When it is bound to two metal centers, it is called mu 2, and it can bind as a Cr3 when it is mu 2 alkyl. It can bind to two metal center as Cr2, it is called mu 2 alkylidene, and when it is bound to 3 metal center, it is called mu 3, and since Cr is being bound, it is called mu 3 alkylidine. Similarly, there is a lot of diversity observed in binding when it is sp2. Like the sp3 center, sp2 also has a rich type of binding, which is can be as metal bound to an aryl group, where the center is an sp2 center carbon binding to the metal, and these are called aryl. This being a terminal binding, it can be classified as terminal ligand. Similarly, this aryl group can also bridge and show a bridging binding, the way it is shown here. Similar to what we had observed for the alkyl binding, this is designated as 3 center mu2 aryl. There can be a direct carbene ligand having sp2 hybridization bound to the metal, and that can be designated as R2. So, these are called carbene or alkylidene. This is a terminal carbene bound to the metal center. Similarly, a sp2 carbon in the form of carbene can bind in a bridging fashion, with Cr2 being a Cr moiety. The way it is shown here, and then it is called mu2 alkylidine. Alkylidine with dy and mu2. C2 fragment can also bind in a terminal fashion as shown. This is called a vinyl ligand. The terminal vinyl binding is shown here. Likewise, there is a mode which also show a bridging binding, bridging vinyl binding. Now, based on the previous way of naming these bridging modes, a bridging vinyl thus would be written as mu2 vinylidene. There can also, instead of olefin, there can also be a carbonyl moiety having sp2 center binding to a metal center, the way it is shown over here. And these are called acyl ligands. So, what we see that sp2 centers of various organic moieties as shown over here as well as over here that bind to metal center in two types, mainly bridging as well as terminal. Also, what comes to the fore by looking at various kinds of bridging and binding, terminal bindings for the sp2 center, and then comparing the same with the earlier discussed sp3 ones, then it becomes obvious that the sp2 center has a rich diversity of binding modes. That is something which is important to remember, and many of these sp2 carbon binding are important intermediate in many catalytic cycles. For example, in olefin metathesis, hydrogenation, polymerization reactions, many of which have gone on to become hydroformylations, many of which have gone to become blockbuster industrial processes that has millions or probably $1 billion of turnover annually throughout the globe. So, from this it can be gauged that these compounds are extremely important from the catalysis point of view. Now, let us look at the third type of sigma donor ligands, which are carbon having sp hybridization. Now, here one can have a Cr moiety bonded multiply to a metal center. These are very interesting compounds and are called carbines or alkylidins. Please, unlike with that of Cr2 where it had been carbene, in carbine the B is replaced with Y and alkylidine is replaced with Y. The carbine can also bind in a bridging fashion. So, this is terminal type. The carbine can also bind in a bridging fashion. Which can be shown as like this, and this is called mu2 sigma pi alkynyl. So, this sigma is this bond, designates this bond, and this pi designates this bond. So, the alkyne moiety bridges between two metal center by two kinds of interaction. This is very unique and kind of very special. One type is a sigma type, another type is a pi type. Like metal alkaline, there can be another type of CCr, and these are called alkynyl. Metal alkaline can also be a terminal as shown over here and can also be bridging. As is shown over here. So, this is again 3 center mu2 alkynyl. And lastly, of sp type, there can be terminal bonds like this, and these are called vinylidene. So, to summarize today's lecture, what we had seen is we have seen through the various binding modes of carbon ligands, sigma donor ligands, and what we saw that a rich diversity of binding can be observed depending on the hybridization of at the carbon, that can range from sp3 to sp2 to sp, and most of these bindings can be classified into two types, terminal and bridging. And of the three hybridized centers, the sp2 probably shows a rich diversity in binding. And lastly, I must note that these binding are extremely important in understanding the crucial interactions that happen between the metal and ligand in this compound, as this compound play a significant role in chemical catalysis, and hence their reactivity can be understood by understanding their binding. So, with this I would conclude today's lecture. Look forward to taking up the next lecture, which involves synthesis, preparation, property and stability of this kind of sigma alkyl complexes. So, a lot more to learn about what kind of reactivity these sigma alkyl complexes displayed by virtue of their binding to metal, how they can be prepared, what are their uses, and so on and so forth. So, I look forward to being with you in the next lecture, and with that, thank you for being with me in this lecture.